Hello, everyone. This is Kamini Jagtiani, and I'm the Senior Engineering Manager for the Nickel Query team. Thank you for taking the time to attend this presentation. So Couchbase, as you know, is a NoSQL database with an exceptional query language called Nickel. All these years, when you use Nickel to either insert, update, delete, or select documents from the database, you got Atomicity, but it was at the document level. Now with Cheshire Cat or 7.0, which just got released, we've introduced ACID transactions into Nickel, and that's what this presentation is all about. So going right ahead. So the agenda is we are first going to talk about how our transactions actually look, how they compare with the RDBMS transactions that you're very familiar with. We'll talk about the workloads we are able to handle, and then we'll go into a little bit of detail as to how we've gone about implementing it. What does it mean for you? How do you debug, configure, and then a whole lot of demos and whole lot of examples. So let's get started. So how does a TPCC transaction? TPCC is one of our performance measures, which RDBMS uses very widely. So how does a TPCC transaction look in MySQL? Now, this is the delivery transaction of MySQL. You see, it starts with a start transaction. It ends with a commit transaction. And then in between, you have a bunch of selects, deletes, and updates. You also set an isolation level of read committed. And this is how the familiar delivery transaction of TPCC looks. Now, how does this delivery transaction look in Couchbase in Nickel after the ACID has been introduced? Ta-da! This is how it looks. Exactly the same. We have the start, we have the commit. We are able to set the isolation level to read committed, and then the selects, the same syntax for updates and deletes. It's exactly the same syntax. So if you're used to writing or using transactions in RDBMS, there will be absolutely no difference in Couchbase syntactically. Moving on, seeing another example. This is the new order transaction, and this is how the performance is actually measured in TPCC. The number of new order transactions is the TPMC that you measure. And this is a very long transaction that's actually there. It has loops and a lot of selects, a lot of updates, and a lot of inserts. But just for the sake of limited space and so that it's clear, I have edited out a few selects. So I have kept the start transaction, commit transaction. There is a select, there is an update. After the select, there are multiple selects, then there are multiple updates, the inserts, and then the commit. So now let's take a look at how the new order transaction would look in Couchbase. And very, very similar. We still have the start, we still have the commit. The select looks exactly the same, the update looks exactly the same. What's slightly different are the two inserts. You see, we have key values, so we need to have the key generated, which is unique. The rest of them look similar. You are inserting 4685, 2 and 1. Here also you are inserting 4685, 2 and 1. And the same way with order line. So then what am I trying to say? What I'm trying to say is if it looks like a duck, if it swims like a duck, and if it quacks like a duck, then it probably is a duck. So if it looks like a RDBMS transaction, if it handles loads like an RDBMS transaction, it is a RDBMS transaction, but this is for Couchbase. So that's what. So if you were looking at trying to use transactions with Nickel, this is it. It looks very, very similar to RDBMS. There's no new learnings that you have to do. And that's what I was trying to get at in my first two slides. Let's talk a little bit about the takeaways. So what takeaways do we have from here? So Nickel is SQL for JSON. Nickel transactions, which is this, is very, very easy to understand. And as you know, Couchbase is a distributed system with multiple services like key value, query, analytics, indexing, eventing, and so on. Each service could be present on all these services could be on one node, or they could be spread out on different nodes. You could have one query service, or you could have multiple query services. So all this complexity of distributed system is hidden in Nickel transactions. You wouldn't know. For you, it would be just one system. And my next slide will talk about the workload and how this is designed for modern scale-out systems. We definitely handle all the relational and NoSQL workloads. And the Nickel transactions support select, insert, update, delete, and merge. So all DML statements. Moving on. So let's talk about different workloads. So typically, suppose after all this COVID ends, you want to go for a vacation. This is a good time to start planning for one. So finally, when you start looking for a vacation, you will find it will finally culminate into a transaction, which is maybe buying a flight ticket, booking a hotel, reserving your car, right? Those are going to be the ultimate transactions. But you won't arrive at the transactions immediately. You will go through a bunch of processing, like searching for different location, looking at the COVID numbers, looking at the safety, looking at the cost. And so all those are called as interactions. And the system that handles it is called system of interaction. So, so basically, before you reach to the transaction stage, which is actually buying, reserving your flight or reserving your hotel, you go through a bunch of interactions. Now, Couchbase all this time was the system of interaction, which would take you all the way to transactions and let somebody else do the transaction. Now, finally, after the asset semantics in Nickel, we have become both the system of interaction and system of record. So which is why I said in the previous slide that we are designed for modern scale-out systems. Typically, we have seen with customers that it takes about thousands of interactions to get to one transaction. Now, with Couchbase able to handle both the loads, you could use Couchbase both for system of interaction and system of records. And that's about the workload. That's as far as marketing for Nickel transaction goes. So now let's talk about a little bit of detail as to how we do it. Like I said multiple times, Nickel transactions is multi-everything. You saw in some of the previous slides. You can have multiple statements between the begin and commit. So so Nickel transactions includes multi-statements. These statements could work on different documents, so multiple documents. Each of those documents could belong to different collections. These collections could be part of different scopes. Scopes could lie in different buckets, and you can do the Nickel transactions using various APIs as well as tools. You could do it using UI. You could do it using CBQ shell. You could do using REST API. You could also do using Java SDK. And so it's multi everything. Also, there is no central coordinator. So if you have one query service, and you can have about 100 transactions running on that query service. If you add 3 query services, you will have 300 transactions that can run on this query service. So it scales pretty linearly because there's no real central coordinator. And we have, towards the end, I have a slide with TPCC numbers, which shows how well we scale linearly. Also, there is, like I said, supports all or nothing for multiple documents. That's the asset semantics. And yeah, and let's quickly take a look at a simple example right here. We covered the more complex examples, TPCC examples, in the first 2 slides. So now let's look at a simple multi-statement transaction as to how it looks. So it starts with the start transaction. It ends with a commit or a rollback. Now the first statement that has come in here is update customer set balance, where customer ID is 4872. Now, when the query service receives the statement, it will look at the where clause and decide an index which will serve this query. So typically that index would be with the leading key CID. The indexing service will then look at the CID equal to 4872, and it will return the document ID or the meta ID back to the query service. The query service will take that meta ID and fetch that document from the KV service into the query. It will then update the balance. So it will increment the balance. And now, so if there was no transaction involved, this document which was updated would be sent back to KV, would be sent back to KV and the update would complete. But now, because there is a transaction involved, this document will not directly go to the KV. What will happen is it will go and sit in a delta table. There is one delta table created per transaction per collection. So as soon as you, when you hit the start and before the commit, for the first mutation, as soon as you hit the first mutation, we go and create a delta table, which will hold all the mutated documents of a transaction. So this customer document, which we just updated for customer ID 4872, instead of going down to KV, will be stored in this delta table. Now, when the next update comes, where we are trying to debit the balance, again, it will look at CID. It will pick the same index as it picked for this, for the first one, and it will send the indexing service will then send the meta ID of this new document. But now, when query service receives this document, it will say, oh, hey, there is a delta table for this transaction. So first, it will take a look at the delta table if this document has been mutated by this transaction. And in this case, it has not been mutated. So it will go back and fetch from the KV another document, decrement the balance, and then keep that document again in the delta table. So that's using this delta table is how we provide read your own writes. And you're seeing that so far, we have not really gone and written this document to KV, right? So if there was another transaction which was going on, it could be working on the same set of documents, and nobody would try to stop it, because until you go and write to KV, there is no real lock being taken, right? So that's why we say that it is optimistic concurrency with read your own write support. Okay, now when the third statement comes in, which is the select statement, it'll take a look. It'll again see where CID in 4872.1924. It'll pick up the same index, go all the way to the indexing service. Indexing service will return the two meta IDs. And now the query service will see, oh, both these documents, both these meta IDs are present in my delta table. So it can return, it doesn't need to fetch anything else from KV. So it can return the output right from the delta table. Now, when you next hit commit, that's when all those mutated documents which were there in the delta table go down to the KV. They get saved in the XAtters, and from the XAtter, and there actually the actual checking is done where has somebody overwritten these documents? Has somebody written to these documents before, after my transaction started, or after I have read? And if something like that has happened, then this transaction will be rolled back. So that's what's happened. So only when you hit commit, you're trying to write the documents down to KV. So you can see from begin, update, select, all this time, we read the document from KV, we updated the document, and we held it in the delta table. And only at the commit time, there is an actual write happening, and there is basically a lock being taken at that point. So until that point, it is all optimistic concurrency. After that time, it becomes pessimistic. So the whole nickel transactions is a good mix of optimistic and pessimistic, and optimistic being for a longer duration. So that was about this slide. So what does ACID? You are already probably aware of the acronym ACID for RDBMS. It's pretty much the same. We hold the same semantics for nickel with slight variation because it's a distributed system. And we try to hide the complexity of the distributed system. So what exactly is ACID, or what exactly is transactions? So transactions, in my opinion, is just, or in everybody's opinion, I think it's a pretty well-known fact that transactions are basically multiple read and write operations which need to be protected. That's why you are putting them as a transaction. So far, when we didn't have the ACID semantics, you could have statements which were modifying documents, separate from each other. But when you want a set of documents or a set of operations to either happen completely or not happen at all, that's when you want to put it in transactions, or put it in between begin and commit. So the first property for ACID is atomic, wherein again all or nothing for each statement and the whole transaction. So if your transaction was to debit from your savings account or transfer the money from your savings account to your checkings account, then in that case, either both the debit and credit would happen or neither of them would happen. Also, I noticed that I say for each statement. So this is called statement level atomicity. So if suppose there was a problem in your statement, maybe a syntax error, or maybe something that's not supported by the system, then in that case, the transaction doesn't auto roll back. The transaction reverts the effects of that statement so far. That's why we say all or nothing for each statement, and it's called statement level atomicity. The next part of it is consistency. Typically, consistency talks about taking the system from one consistent state to another. And the only and in RDBMS, you have many constraints, like you could have the unique key constraint, or the not null constraint, or the foreign key constraint. But in Couchbase, we have just one constraint, which is that the document key needs to be unique. Isolation is the third one. We use read committed isolation, and that's the only isolation we actually support. And that's the most common one, even with RDBMS. The scan consistency, now, as you know, in case of Couchbase, the data and the index do not reside together. They are separated out. Which is typically how it is. Even in a library, you have the index somewhere, and then you have the book somewhere else. So you have your data and your index separated out. Now, so that's why when we commit, we are committing the data. It takes some time for the indexes to be updated. And so by default, our scan consistency is request plus, which means that the indexes will be updated to the recent most mutations. If you want a faster performance and do not really care about a slight amount of staleness, then you can get that by tuning it with unbounded. But in either case, whether you use unbounded or whether you use request plus, there are no dirty reads. Now, durability is where we handle the complexity of the distributed database. So there is a primary, there are multiple replicas. Now, durability is one property. It's like in Vegas, you say what happens in Vegas stays in Vegas, right? Same way in durability, what has been committed once has to remain committed no matter what. You might lose power, you might lose a disk, but what has been committed or what has been written cannot be undone. So you do that by writing not just to the primary, but also to the replicas. So there are 3 durability levels that we support. The first one, and the one which we use by default, is majority. In case of majority, so a transaction commits successfully only when the changes that have been caused by the transaction are written to the cache of primary as well as majority of the replicas. So say it was a 4-node system with 1 primary node and 2 replicas, then majority would mean that the changes which have been caused by the transaction would be written to the cache of primary and at least one of the replica. Second one, majority and persist active, is the one in which the transaction would be successful or would return successfully only if the changes have been committed, or only if the changes have been written to the cache of majority of the nodes and persisted, that is gone to the disk of at least the active node. So in this case, it would mean that it would go onto the cache of 2 nodes and onto the disk of 1. Persist to majority, as the name suggests, it should go on to the disk of the majority of the nodes. So persist to majority will be the slowest, majority will be the fastest, and our default is majority, and it is easily tunable, and I can show you later how to tune it. Okay, So far, when I was showing you all these transactions, it appeared as if those transactions were being fired off from CBQ or from UI. But the nickel acid support or the nickel transactions is also very well supported by SDK. So far, Java SDK supports nickel transactions. .NET SDK with support for nickel transactions should be coming out very soon, followed by other SDKs. So this is a quick example of how you would use nickel transactions using the Java SDK. You first create, let me just move this here, okay. You first create a configuration, and here you're passing the durability level as majority. Of course, you could do persist to majority, or you could do majority and persist to active. You could give either of those here. I'm also setting an expiration time of 60 seconds. The next thing is we are creating a transactions object. And then this is the Lambda function of Java SDK. And they've added, Java SDK has added a query method to it. So you give ctx.query and you provide the query statement as you saw in the previous slides. And then when you close the try block, it auto commits. You can give a separate commit. If you don't specify a commit, it will auto commit. And all the errors that could happen in this get captured in the catch, right? So this is how this would be a simple example using the Java SDK. Okay. This is another example of support through Java SDK, but this has KV transactions as well as nickel transactions. So KV transactions were went out as part of 6.5, and you could do it using the SDK. At that time, we did not have the ACID support in nickel, but now both KV transactions as well as the nickel transactions can exist harmoniously, and they work wonderfully. So again, you have the configuration setup wherein you're giving majority and the expiration time. You're creating a transactions object. Now you're starting first with the KV transaction where you're getting the customer document. You're replacing the new address inside that customer document. And then within the same transaction, you're having these 3 queries, and then you're committing. You could have a KV transaction statement followed by nickel transaction. You could have a nickel transaction statement followed by a KV. Mix and match KV nickel. It should all work. It's all been well tested, and like I said, it's currently supported by Java SDK. .NET should be coming out soon, and there are more SDKs on the roadmap. Here is an example of read your own writes, statement level atomicity, write your own writes or cumulative writes. So remember I talked about the delta table. The delta table is created per collection, per transaction. So now when you get the start transaction, that's where your transaction starts. It returns a transaction ID, which is unique, which identifies the query node which has been selected to run this transaction. And all the statements which are between the start and the commit need to go to the same query node because they have to read and write to that delta table, right? So the start transaction will return a transaction ID. Update employee set salary where performance rating is 1. When this statement comes to the same query node where start transaction was given, it will look at the where clause, which is perf rating equal to 1. Select the right index to serve this query, and go to the indexing. The query will go to the indexing node. The indexing node will send the meta IDs of all the documents. Will send the meta ID of all the documents to the query node. And then the query node will perform this operation on all those documents where it will update the salary or increment the salary of all those documents and store those multiple documents which are mutated as part of this transaction in the delta table. Now, when you do select employee ID, name and salary from employee, and you're giving the same where clause, it will select the same index. It will again go back to the indexing node, which will return back the meta IDs. But now when it looks into the delta table, it will see that all those documents have been recently mutated as part of this transaction. And so it will return the results right from the delta table. So that's how we do read your own writes are done via the delta table. The second example is a slight modification of the first one, where you have the start transaction, you have the salary updated, and then you're also incrementing the year when the salary was last updated. So when the first statement comes, it gets those documents, updates those documents, keeps them in the delta table. When the second statement comes, it looks at the same at the same where clause, finds the index, gets the meta IDs, finds all those meta IDs in its delta table, and re-updates all those documents. But this time it's modifying the field increment year and setting it to 2021, and again keeping it in the delta table itself. Then when the select comes, again it's with the same where clause. So the indexing service will return all the meta IDs. It will find the meta IDs in the delta table, and then it will return the customer ID, name, and salary from there, and finally commit the transaction. So this was an example of read your own writes, which are done with the delta table. Cumulative writes or write your own writes are also done with the delta table. The third one is statement level atomicity. So here we see that there is a start transaction. You're inserting into employees a key and a value. Then your next statement, you're again inserting another document with key and value, but then you're keeping the key as the same, which is not allowed. We have a unique key constraint, right? So at this point, the transaction doesn't auto roll back. It just returns an error, keeps the transaction open. If there were any changes which were caused by this statement, only those would be reverted back. And the transaction would continue. It would be up to the user whether the user wants to commit or roll back. In this case, the user quickly realizes that by mistake it inserted the same key, so it updates to key 11, and then inserts that document, and then finally commits. So this part is implemented using the transaction log, the in-memory transaction log. So per transaction, we are not only creating delta table, we are also creating an in-memory transaction log. There are two things which are created per transaction. Okay. Now this is an example with save points. So save points are very necessary, are actually used quite a bit in RDBMS also. And save points are also implemented using the in-memory transaction logs. And this happens like you're doing a bunch of inserts, updates, deletes. At some point, you realize that you didn't want to do what you did. So you can always revert back or roll back to the previous save point. So in this case, you're seeing we are inserting three. There's key 0, key 1, key 2, 3 documents. And then we are setting that with the save point S1. Then we are updating. We are setting the years of experience to 10 when the age is greater than 30. So for these two documents, you would set years of experience 10. You keep that as save point S2. Then you're setting more fields for age greater than 0, which is B and C, B to 10 and C to XYZ. And very, very soon after that, you realize that you don't want to do this. So you roll back to save point S2, which means this will be reverted back. The statements between S2 and the rollback would be reverted back. And then finally, you're committing. And I have examples too. I'll show live demos to all these things. So it should just get more clearer at that point, hopefully. Okay, so all this time when we talked about here with the delta table and the transaction in memory log, you must have realized that if there are multiple statements between the begin and the commit, then you would have so many mutations which were being saved in the delta table, which is in and delta table and transaction log are going to be in the memory of the query node or query service. So basically what happens is those keep accumulating, and so that can increase the memory consumption with the transaction. So typically when we do transactions, all of these transactions are supposed to be short with less number of mutations. But there are many use cases where you want mass updates, like suppose your management decides to give a raise to everybody, right? And if there are 500 employees or if there are 5,000 employees, then you want to do these mass updates, or you want to do mass inserts and you want it such that either all of them go through or none of them go through. So you still need the asset semantics for these mass updates, deletes, inserts that need to happen. But if you would use the multi-statement transaction, which I showed you before, then that could cause a lot of memory bloating with all the mutations being stored in the delta table, with the transaction log being generated. It's possible that you would hit out of memory kind of condition. So for such single statement transactions with mass updates and mass deletes, we simply set a parameter, a query parameter called tx implicit, which will provide all the asset semantics. That means all your updates would either go through or not go through. But in that case, we are not creating a delta table or the transaction log. We are making the changes, and as you make the changes, we are invoking the commit protocol, and the changes are being saved in the XAtters of the documents. And only when you finally are done with all the changes, those changes start getting copied over. So you're still getting the asset semantics without bloating of any memory. And again, all of the DMLs can use this. Next one is best practices. So for best practices, the default scan consistency I said was request plus, because we want the indexes to have been updated to the latest mutations. But if your workload is such that you don't really care about slightly stale data, then you can get better performance using unbounded or not bounded. We provide the read your own rights using the delta tables, but even though that's provided, you have to realize that your delta tables can occupy memory in the query node. So you have to limit the number of updates that are happening in the multi-statement transaction. If the number of updates are going to be very high in thousands caused by a single statement, then in that case, let's make sure that we are using the singleton transaction, which is tx implicit. All the updates again are optimistic. So now you can imagine that if there are, and I'll show a demo on this, if there are multiple transactions happening in parallel and they are all working on the same data set. So the transaction 1 is modifying 10 documents, transaction 2 is modifying 5 out of those 10 documents, then the one which commits first gets committed. The other one at the commit time will realize that the documents have been written after we read. And so this transaction will roll back. So if you have a lot of transactions which are working on the same data sets, then you can see rollbacks. One would commit, others would roll back. Also, you want to make sure that you're not doing non-transactional writes on the same documents that are participating in transactions. And like I said before, multi-statement transactions are lock-free, coordination-free, designed for complete scale-out. Yeah, that's the, okay. Getting to the monitoring, debugging, and configuration, you can always monitor how much memory your transaction is taking by looking at system transactions, doing select star from system transactions. That will give you durability level being used, isolation level, scan consistency, memory that's being consumed by the delta table and transaction log, and so on. Per transaction, you could also have certain configuration parameters. You could configure TX timeout. You could configure again TX implicit, which was for single statement transaction. Durability level could be set to majority or majority persist active, or all persisting. Scan consistency could be set to unbounded or request plus. If you set the scan consistency to add plus, then we auto upgrade to request plus. And TX ID. Okay, so TX ID is the special one here. Now, TX ID, I told you that when you start the start transaction, Oh, I also forgot to mention, you could also call it begin work, start transaction, or a begin transaction. The three, or all three can be used. So when you do a start transaction, you get a TX ID. That TX, so, and all the other statements need to go back to the same query node. So somehow with every statement, we need to tie to the same transaction. That tying is done using the TX ID. Now, if you use the CBQ shell, that automatically takes care of it. If you use the UI, that automatically takes care of it. If you use the SDKs, they automatically take care of it. But if you're doing a transaction using REST APIs, that's pretty stateless. So when begin transaction returns a TX ID and you want to send an update as part of the same transaction, then in that case, you also have to send TX ID to identify that this update or this select or this insert is part of the same transaction. And that's where the TX ID is used or can be configured. The last one is ATR collection. ATR collection is, so ATRs are active transaction records used by our commit protocol. And they are, you can take them as metadata. So ATR collection, if you set to a specific collection, then all the metadata ATRs that are generated by commit protocol will go into that specific collection. If not, they are stored in the default collection. Okay, here are the TPCC. So we ran TPCC in Python, pytpcc, which is very similar to the TPCC and just written in Python. And it was also run by MongoDB at some point on single node, but we ran it across multi nodes. Now here I've taken the durability majority, and we've taken scan consistency request plus as well as not bounded. Of course, I told you not bounded will perform better than request plus, but this is our default configuration, majority and request plus. So this is for 100 warehouses. For one node, we saw 8,880 new order transactions getting done. Now, you look at, so when you go from one node to two nodes, you don't see a whole lot of difference because the distributed nature kicks in. But what you should compare is if you look at 2 nodes and 4 nodes. So if you had 2 nodes, and then if you had 4 nodes, you're seeing that it is doubling. This is approximately 9,000 and this is 18,000. Similarly, if you compare 3 nodes and 6 nodes, again, 13,500 new order transactions and 25,140 transactions. And these are all with 2 replicas. So you can see very linear, you can see a pretty good coordination free scalability, modern scale out system kind of thing here. With 2 nodes, you're getting 8,900 transactions. With 4 nodes, you're getting 18,300 transactions, and so on, right? So this is what we wanted to show here. Yeah. Okay, so takeaways again. Nickel SQL for JSON. As you might have realized, we are designed for scale out. We are very easy to understand. We are very nicely hiding the complexity of distributed system using the TX ID, using the durability, using the scan consistency. There is not much that you need to change in your application when you move to Couchbase, because Nickel provides very similar syntax. Again, it's for modern scale out systems which can handle both RDBMS as well as NoSQL workloads. And we support all DML statements: select, insert, upsert, update, merge. We also do select, prepare, and explain, though it never you should never really be running prepare or explain within a transaction, but those are allowed. Those are acceptable DML statements which are allowed in transactions. Next, I'll be moving to demos using CBQ Ui, and I'll also show something called as the transaction simulator that we have that we have developed, so that you can offline run through that simulator and see how the transactions are working. So let's quickly look at the demos. I have two sessions which are open here. And I'll just show you alias KCBQ. This is just starting a CBQ shell. I'm connecting to my local machine, and this is my user ID and password, which I shouldn't be showing you, but then anyways, KCBQ, and here is another one. So I have not create. So what I'll do is, you probably are already familiar with the collections feature. In this case, I'll first set the query context. So here what I'm doing is, this is employee 1 is my bucket, and scope 1 is my scope. I'll set the timeout to 10 minutes just because I'm going to be doing a lot of explaining. So this is the timeout. Now, if you're familiar with CBQ, it shows a bunch of JSON related syntax. Like I can show that and then turn that syntax off. So I'm going to go ahead and create a brand new collection, which is create collection. And you see, it will show you a request ID, it will show you a status success, and it will show you a bunch of metrics. Typically, you don't see all of that when you use the PostgreSQL SQL. So I'm going to go ahead and turn off the metrics and signature. So with that, it's been turned off. Now I'm going to insert just one document into my collection, and you will see that it has been inserted. I'll go and create an index on the age. And this is all outside of transactions. So we have been able to create the index. Now this is my session 1. And this is my session 2. So there should be session 1 somewhere here. I should edit the title to session 1. Okay, session 1 and session 2. And then, so I'll do the begin work. You see, it returns this TXID. But because this is CBQ, it does the auto stitching. You really don't need to worry about anything. Now I'm inserting another document with key 1 and age 45. Right? Now I'm going to select to make sure. So you know that now we should have 2 documents here, one with key 0, one with key 1. Right? So you see 2 documents, one with key 0, one with key 1. But now this is in session 1 and this is begin work. I haven't yet committed. Now this is session 2 where CBQ is on. I'm going to set the query context to scope 1 and timeout as 10 minutes again. Right? Now, if I'm doing a select here, since this has not committed, you really shouldn't be seeing this 45, this document. So let's see. Okay. See, you see only one document 40 with the age 40, which was this one, key 0, age 40, because this has not been committed yet. Now I go back to session 1, I update, I go and add the years of experience. Right? And now again, I select. So you will see that for both our documents, this new field would have been added, years of experience. But here, it would still be the same. You see, it's not been added here and you're still not seeing key 1 here. But as soon as I hit commit work here, this is committed. I go and I do. Now you're able to see both the documents and you're able to see the years of experience. So you're seeing that there is this isolation, right? There were 2 transactions which were running in parallel. But because I had not committed in session 1, you couldn't see what was happening in session 1 in your session 2. So there is no dirty reads here, right? That's what I was trying to exhibit. Also, remember, I showed you the duplicate key thing. So let's try to see it here. I'm doing a begin work. I'm inserting an employee with key 10. So we already have key 0 and key 1. I'm inserting with key 10 with age 50. I'll again try to insert. Let's change this to 55 when we do it. So then you will know the difference. 55 and now insert into employees key 10. Now this should fail because when it inserts, it will look into the delta table that the key, since it's part of a transaction, the first insert would have actually made a change and caused the mutation in the delta table. So when you do the insert into this employee, you'll say, hey, duplicate key, because it finds that in the delta table and realizes that you are basically your constraint is getting violated. So that's the consistency property. So it failed, but you see, it didn't auto roll back the transaction. It left the transaction open for me. Now I can go and say, hey, let me go and make this key 11 because I typed 10 by mistake, and then it's successful. And if you go and see here in the second session, you should not see any of these. You should only see key 0 and key 1, and which is what you see. Now at this point, I'll go and commit. It's all committed now. So now you should see key 10 and key 11. Let's do it here. You see key 0, you see key 1 with years of experience 10, and then you see key 10 and key 11 where we never added the years of experience. Now I'll show you an example with cache mismatch, which is when two transactions are working on the same set of documents. Remember, I said that in one of the slides towards the end, I said that if there are multiple transactions working in parallel, since it's optimistic concurrency, there's nobody stopping them from working on the same documents. But at the commit time, it will be realized that that the document has been overwritten or has been written by another transaction after I read the document. And so at that time, the transaction going in second will have to roll back. So let's try this. We'll do a begin work. We'll update the years of experience to say 20 for age greater than 30. Right? And now you will see how many documents have been modified by it. All the documents have been modified. We have updated, all of them were over 30. So we went and updated this. Now let's go, let's not commit this transaction. Let's go and start working in a second session. Begin work. Oh, see here, I didn't turn off the metrics and signature. So you see all this other JSON related stuff that comes in. Then you do update. So now here we updated and we added years of experience as 20. Here we updated and we added the years of experience as 25 for again the same age group. So it's working on exactly the same documents. We'll go and select. So you see here you have key 0, key 1, key 10, key 11, all with years of experience 25. This is not committed. In this session, it's key 0, key 1, key 10, key 11, all with years of experience 20. Now, if we go and commit this transaction, which came in later first, then this will commit. So it's committed. You can see this is, it took the years of experience as 25. Now let's try to commit this. What happens? When now you try to commit this, it says key already exists or cache mismatch. This is the important thing here, cache mismatch. This means that there was another transaction which modified the same one or more of these documents that you were trying to modify and committed before you did. So, so commit transaction statement error, which means that now if you re-execute the whole transaction, you are free to go and retry the transaction, or maybe somebody else modified what you wanted to already modify. So you will try to do a select and you will see that the years of experience is 25, which was done by this transaction. And so now if you want, you can re-execute your transaction, make sure everything is correctly done. Like you can go ahead and do this again, because you want to change it to 20, not 25. So you'll do this, but make sure you commit immediately. And this time your transaction is successful because nobody else modified your documents. Okay, here's an example with save points. Let's do this. Begin work. Okay. Now you're inserting key 2 with name John, age 50. Sorry, I missed the I. Here, this is inserted. I'll select and make sure that we have all the data. So it should be key 0, key 1, key 10, key 11, and key 2, which is what you have. Key 2, key 0, key 1, key 10, and key 11. I'm going to put a save point right here to show you how it works. Okay. Now I insert more documents, this time with the name Walker or Walker. Again, I'll select. And you see these 2 new are added. Then I realize I don't want this new Walker or Walker here. So I go and roll back to save point. So which should take me back to this place where John was inserted, but not Walker. So roll back to save point, initial save. We go and do a select. And you will see John is there, but there's no Walker. Now at this point, I decide I don't want either of them. I don't even want John. So let's get rid of that. Roll back. I roll back. So now I'll go and do a select. And you see we are back to our same key 0, key 1, key 10, key 11. So that's how rollback works. That's how rollback to save point works, right? So now I'll show you. We talked about the implicit transactions, right? So I'll move to I'll set tx implicit to true. Now I want to show an update to multiple documents that are happening. So I'm going to set it to TPCC because there's no point in showing you these 4 document updates. So I'm going to set my context to TPCC. And now let's look at select star from customer where C balance is -10. You see that there is this is the document, customer document. It has C balance, C city, and so on. It also has an extra field, extra 1, extra 12, extra 15. And let's see how many of such records are there. You have these. There are 30,000 such records with C balance equal to -10. Now, if you wanted to update these 30,000 documents, you don't want to do a multi-statement transaction with a begin work and update and commit, because all those 30,000 documents would be considered mutations, growing your delta table, holding transaction logs for it. So what you would do is set the tx implicit. I think I set it before, but let me go and set it again. And then, so we saw there was an extra 1, extra 12, extra 15. Let me go and update customer. What happened here? Okay, update customer, set extra 20. There's no extra 20 so far, right? So we go and add a new field of extra 20 when C balance is -10. And we are still doing it with ACID semantics because we have set the tx implicit as true. I'm going to do that. And here is the other window, the other session. If it was not transactions, you would have seen extra 20 come immediately, right? So here I'm going to do select star from customer, and you see there's no extra 20 here. It is extra 1, 12, and 15 because this update has not completed and it's being done with tx implicit true. So it's going to reflect only after all the documents have been updated. So let's wait. It's taking some time to add a new field to 30,000 documents and actually commit. Now it's done. So let's go and take a look here. And you will see extra 20 has been added here. We can see here as well. Extra 20 has been added here. We can change the limit to say limit 10. You'll see it has been added to all of them. That's how it works on CBQ. I can quickly go ahead and show on UI how it works. And oops. Okay. So let me drop the collection first. So the collection that we just created has been dropped, right? So I'll go ahead and create the collection. Again, employee 1 is the bucket, scope 1 is the scope, employee is the new collection, and we execute. Employee 1, and then we select the scope as scope 1. And now I'm going to go ahead and insert like we did before. And this is not with transactions. So I'm just going to do insert, right? And then I'm going to go and create an index. Okay. Now we are going to start a session. The thing about UI, remember again, begin work returns a TXID. UI has to now bind all those transactions into a single transaction. So what you do is you basically put them one after another as a batch transaction, as a batch. And then this was the part, update and commit. So now you have begin work, you're inserting into employee key 1, your select, there's update, there's select, and then there is commit. So I execute and it will all execute as a transaction. You can see the first begin returned a TXID, insert successfully inserted, select gave me 2 documents, 40 and 45, update, updated the documents. Select again gave me 40 and 45 with the years of experience as 10, which we updated here. And then we finally commit. Now, when we finally commit, we can go and run this select star again to see if we are seeing everything correctly. Execute. And there you go. You're seeing the documents without transactions. So when you want to run with transactions, you have to give begin to commit all the statements one after another. That's how it's able to tie the TXID. That's not the case with CBQ. You can keep going down one by one and do it, right? So this is how you use the UI. You remember the TX implicit that I talked about? So let's quickly go. Let's quickly select default and TPCC. Okay, let's actually go here. So there are 2 buckets here, default and employee 1. If you look at the documents, there's default, TPCC, and we were working on the customer document, right? So you can take a look at this document, see balance, we introduce extra 20 here. So you go back here to query. And now what we want to do, we want to, here we don't need to set separately TX implicit. What you could do, you can still do this and see, select count star. Command V, select count star. There are still 30,000 documents. You can see how a customer document looks. Right? It has C balance, C city, and it has extra to extra 20. Now we want to update with the asset semantics, but it's a bigger update. So we want to run. So here, if you're doing it using UI, you don't need to set TX implicit. You can run as transaction. So if you simply do execute, it runs without the transaction mode. If you do run as transaction, let's change this to extra 25 this time. If you do run as transaction, it will run. You can try here if it comes extra 25. See, there's no extra 25 added yet in the next session. Okay, results. Let's try here. See, extra 25 has been added. You can even go back to the documents here. Take a look. See, balance is -10. So this document would have gotten updated and extra 25 is there. So what I wanted to show you also was, let's make this extra 30, but not as a transaction. So when you're now, when it is extra 30 and you're updating the balance, if you don't want to run it as a transaction, you will just do execute and it will start executing. And you could probably see an extra 30 already, see, even though this is not over. That means that it's happening per statement, it's happening per document, right? When it completes, all of them will happen. And see, this is much faster because it doesn't need to go and save those into the XAtters and stage it and then make sure that the cache is okay before copying and so on. So all the asset semantics are not there when you're just doing the execute. If you want to use execute and you want to use the multi-statement transactions, it has to be between begin and commit and then run execute like I showed here. Yeah, see, begin work, insert. If we take this, if you do this, then you can run the execute and you will be fine. Run as transactions is to be used for TX implicit. I know this has been a lot of information to digest. So we have also gone ahead and created a simulator, which is simply https transactions.couchbase.com. And what this does is it shows you how transactions work internally for us. So let me just quickly run through this before ending the presentation. Credits where they are due. It's based on the Aries simulator work, which was done by UC Berkeley, but we have completely rewritten the JavaScripts and everything. But the idea is based off the Aries simulator, which was done by UC Berkeley, guys. Here, so you start with the begin work. When you start with the begin work, there's a TX ID which is created. When you insert, there's a delta table which is getting, you get the document in the delta table with a cache. Now you roll back, nothing goes to the KV, it's simply rolled back. You start again, insert another value, right? You insert with the same key again, it will do cache mismatch. It will tell you, hey, duplicate key. You cannot have you cannot have it. You cannot insert this, but you can still continue the transaction. See, the transaction ID still is there. Then you do the save point. You insert now for employee 2, employee 3. You do another save point. See what's happening. All the things are getting stored in the log. So there's this delta key space as well as the log which is being created for the same transaction. I'm updating. I'm deleting. Now I want to roll back to the save point 2, right? So save point 2 is here. So that means I want to get rid of this update and delete. So we go here, we roll back and see, that's gone. You insert another one, insert another one. Now when you commit, just watch the KV and the index. So you insert. Now when you commit right here, things go from the delta space into your KV and a delayed entry into the indexes. Now there are 2 sessions. This one was session 1 and this is session 2. You get begin work here. You start begin work here. So what's happening is there are 2 delta key spaces being created. One for session 1, one for session 2, 2 logs being created. You execute in session 1, update in session 1, update again in session 2, update in session 2, but now you commit the session 2 first. So this makes it, this should fail and it fails. Okay. You again do begin work. So you get the idea. So this is the transaction simulator, which is showing you delta and log getting created for every transaction, every session. It's also showing you the impact on KV and how the indexes are slightly delayed. But you get the idea. You can try this out. You can go through it. You will get a good idea of how it has been implemented. Going back to my slides. So this was the last part that I presented. I presented using CBQ Ui. I also showed you the transaction simulator. And that's about it. So the takeaway, again, nickel transactions, if you have used RDBMS transactions, it should be pretty much the same for nickel transactions. And we are handling all the workloads now, RDBMS workloads, as well as the NoSQL workloads. So if you were to use RDBMS, you get only transactions. You really don't get a whole lot of interaction, which is getting captured to give you the personalized, searches and stuff. With Couchbase, you're getting both the interactive systems, the systems of interaction, as well as systems of record. And that's where it ends. Again, I'm Kamini Jakthiani, and I'll be around to answer your questions. If you have any questions, please chat. Please use the chat facility to ask, or ask them however you can. This is my email ID. Feel free to send me an email to get the answers to your questions. Thank you.